Every conversation we have travels as a whisper of light, guided through a thread of pure glass. These fiber optic strands, each finer than a human hair, possess an engineered resilience that belies their delicate appearance, forming the invisible arteries of our modern world. The journey to create them is a marvel of industrial transformation, turning humble quartz sand into colossal coils of cable. These lines are then laid across the vast, dark expanse of the ocean floor, forging the very backbone of our connected age. It began with a single thread, stretching across an entire ocean. In the year 1988, the United States pioneered this monumental effort as the TAT-8 cable went into service, connecting America with the United Kingdom and France. That moment marked the dawn of a new era in global connectivity. From that milestone, the nation became the heart of the world's emerging internet infrastructure. This rapid expansion was made possible by American technology titans like Google, Meta, and Microsoft. These companies are not just users of the internet, they are its investors, co-owning some of the most critical cables on the planet. It leads one to wonder, if fiber optics had never been developed, what would our lives even look like today? It begins not in a sterile lab, but in the dust and grit of the earth. The entire process starts with a single raw material, high-purity quartz sand. Only pristine deposits of white sand are chosen, those containing the exact level of silica needed to produce optical glass. At the mine, tracked excavators relentlessly scrape away thick layers, loading the sand onto heavy trucks. Each vehicle carries dozens of tons, transporting the raw material directly to a nearby processing facility. Upon arrival, the sand cascades onto conveyor belts, where it passes through vibrating screens that shake out larger stones and organic debris. From there, it is moved into vast industrial washing tanks. Inside, powerful jets of water and churning mechanical agitators scrub away any remaining clay, fine dust, and traces of vegetation. This intensive washing cycle is repeated several times until the entire batch achieves the required level of cleanliness. To minimize waste, the runoff is channeled into a recycling system, which recovers fine silica particles carried away by the water. Once the sand meets these strict standards, it is thoroughly dried in industrial furnaces to eliminate all remaining moisture. Finally, the purified sand is packed into sealed containers, ready for the chemical stage, a transformation into the gaseous or liquid compounds that will form the glass preform, the very heart of an optical fiber. It starts as a solid, a material so pure it seems inert. From sealed containers, this raw silica is moved into a chemical processing area, where technicians begin a remarkable transformation, converting the solid into a series of gaseous compounds. Under extreme temperatures, these compounds react and condense, depositing themselves as layers of ultra-pure glass. This is not a simple act of melting. Instead, the glass is constructed one microscopic layer at a time, a method that systematically strips away nearly all impurities. The entire process unfolds within a hollow glass tube, which rotates slowly as a moving torch bathes its surface in fire. As the gaseous mixture flows through this heated environment, it transforms into microscopic silica particles that settle on the tube's inner wall, building the structure from the inside out. By carefully adjusting the gas composition, engineers can dictate which layers will form the light-carrying core and which will become the protective outer cladding. Every layer is controlled with exacting precision, as even the slightest deviation in thickness or purity could disrupt the fiber's ability to transmit light. These stringent demands make the fabrication of this initial rod the most expensive phase of the entire production line. The raw materials require near-perfect purity, and the deposition process can stretch on for dozens of hours for just one piece, driving up costs far beyond other stages. After hours of this continuous buildup, the hollow tube gradually solidifies into a dense, solid rod known as a preform. A typical preform measures between 3 and 6 feet long and a few inches in diameter, yet it already contains the complete core and cladding structure of the future fiber, only on a much larger scale. Once ready, the glass preform is transferred to the fiber drawing tower, a steel structure soaring more than 60 feet into the air. At the tower's apex, the preform is secured and lowered into a specialized furnace where temperatures climb to nearly 3,600 degrees Fahrenheit, hot enough to soften its lower tip. As the glass begins to flow downward, a single drop is pulled into a delicate strand, marking the birth of a continuous fiber. From this moment, the system operates under meticulous control, drawing the strand straight down until its diameter shrinks to just 5/1000ths of an inch, thinner than a human hair. The primary challenge is maintaining perfect uniformity from start to finish. If the fiber's thickness varies by even 1/1000th of an inch, its capacity to carry light could be severely compromised. To ensure this precision, multiple laser sensors positioned along the tower continuously scan the fiber, measuring its diameter with incredible accuracy. Operators may use pliers or small blades to touch or cut the fiber, a necessary step to remove an unstable starting section or to snip a sample for quick microscopic inspection. They also sever the fiber at the end of a run, separating the finished product from the machine and ensuring only fiber meeting the highest standards proceeds. The drawing process can continue for hours on a single preform. From a rod just a few feet long, the factory can produce optical fibers stretching for dozens of miles, with consistent quality and purity, ready for the next phase. Now, a continuous strand, the raw glass is incredibly fragile. To protect it for the journey ahead, the factory immediately applies a protective coating as it passes through a small chamber filled with liquid polymer. This substance is specially formulated to create two distinct layers, an elastic inner coat to reduce cracking when the fiber bends, and a harder outer shell to resist impact and abrasion. Immediately after, the coated fiber runs through an ultraviolet curing system. The intense UV light instantly hardens the liquid polymer, transforming it into a transparent protective shield. This step is perfectly synchronized with the drawing speed, guaranteeing the coating has a uniform thickness and a firm bond. With this protective layer in place, the optical fiber can withstand handling, transport, and testing without the risk of damage. The fiber is then guided through several automated inspection stations where laser sensors monitor its diameter and uniformity, while optical devices measure signal transmission. This continuous analysis ensures the fiber is stable before it moves to the winding stage. At the base of the tower, the finished fiber is fed onto massive reels. Each reel can hold dozens of miles of fiber, wound at high speed while maintaining steady tension. If the strand is pulled too tightly or overlaps unevenly, it can crack or deform. So the entire winding system is precisely programmed and carefully monitored. A mechanical arm guides the strand back and forth, laying each loop neatly side by side in uniform layers, much like winding thread, but on an industrial scale. Operators closely watch display screens for tension and speed, ready to intervene if anything goes wrong. When one reel is full, the system automatically splices the fiber onto the next, so production continues without interruption. In this way, a single preform can produce continuous reels of fiber that are later packed into protective containers for safe transport. From these spools of coated and tested fiber, the factory begins the cabling process to form the finished product. Multiple reels are arranged in parallel, feeding their strands into a massive cabling machine where the fibers are gathered into bundles, ranging from a few dozen to several hundred strands, depending on the required transmission capacity. Between these bundles, manufacturers add reinforcing elements made of steel or Kevlar to increase mechanical strength. Kevlar is particularly valuable, being lightweight yet many times stronger than steel in tension. The entire bundle is then wrapped in additional protective layers. An outer plastic sheath helps block moisture and provide insulation, while some cables also have a water-blocking gel pumped inside to prevent leakage and signal loss. For undersea cables, the construction is even more complex, with multiple layers of steel wires wound tightly around the bundle to withstand deep-sea pressure and resist damage from ship anchors or seismic activity. The cabling machine operates in a precise rhythm, twisting the components evenly around the fiber core to maintain uniformity along miles of cable, as operators carefully monitor the tension and winding angle to prevent any failure. It is a thread of glass designed to last for generations. But first, it must survive a trial by fire, ice, and force. With the cabling process complete, the product now faces a gauntlet of tests to guarantee its reliability for decades. The ordeal begins with fundamental mechanical and environmental trials. The cable is stretched, bent, and twisted to verify its strength, then sealed in thermal chambers that cycle from profound cold to extreme heat. It is even submerged in high-pressure tanks, which mimic the crushing weight of the deep ocean. Next, optical tests send a laser beam piercing through the core to measure any degradation of the signal. These initial steps are designed to rapidly expose production flaws or substandard materials. To truly prove its readiness for the real world, however, the factory proceeds to full-length testing. Engineers connect both ends of the cable to optical transmitters and receivers, sending a continuous stream of data for hours on end. This is not just a simple pulse of light. The system transmits a torrent of video, voice, and network traffic, perfectly simulating actual operation. The cable is only considered ready if the signal travels its entire length without packet loss, distortion, or unusual attenuation. In addition, it is run under a continuous load for extended periods to assess its long-term stability. Some samples are even installed in the field, buried underground, or strung from utility poles, their performance measured again after days of service. This step is crucial, as only through these trials can the manufacturer be certain the cable will withstand 24/7 use for many years. Once the cable has passed every rigorous test, the spool is officially declared a finished product. Before reaching installation crews, however, it must navigate the equally critical stages of packaging and transport. At the factory, the cables are removed from the testing machines and mounted on large rotating shafts. From there, they are carefully rewound into neat coils on massive drums of steel or reinforced wood. Each drum can measure several feet in diameter and hold hundreds of miles of continuous cable. The winding process is performed with extreme care to avoid excessive tension or sharp bends, as even a minor kink could degrade signal performance. After winding is complete, the cable ends are sealed with protective caps to keep out dust and moisture. Every drum is then labeled with its batch number, cable length, structural type, and inspection results. Engineers conduct a final check, ensuring the spools will remain secure during movement through the warehouse. For transport, the drums are loaded onto heavy-duty trucks or into specialized shipping containers. When shipped by sea, they are placed aboard cable-laying vessels, specialized telecom ships equipped with multi-deck storage for dozens of giant drums. Steel securing systems lock the drums firmly in place, preventing any shift during voyages that may stretch for thousands of miles. This entire process ensures that every spool of fiber optic cable leaves the factory in perfect condition, ready to be deployed in projects across bustling cities or laid deep along the ocean floor. The journey across the ocean begins not with a splash, but with a slow, deliberate unspooling. A single thread against the immense power of the sea. The task falls to specialized vessels known as cable-laying ships. On deck, massive drums feed the line into the sea, guided by tension control devices that ensure a safe descent to the ocean floor without bending or breaking. The ship moves slowly, often just a few miles per hour, as it follows a pre-surveyed route. In deep waters, the cable is simply laid upon the seabed. Closer to shore, however, or in areas at risk of anchor damage, plowing machines carve trenches to bury the line several inches deep. Throughout the process, engineers use sensors and underwater cameras to monitor the cable's orientation and ensure it remains free of twists. Once complete, the line rests securely on the ocean floor, linking continents at the speed of light and forming the very backbone of the global internet. A single thread of light, fragile as a whisper, now binds our entire world together. This is a journey that begins with pure white sand and ends with cables resting on the deep ocean floor, a quiet testament to human ingenuity. Each meter of this conduit must pass through dozens of demanding steps on its way to connecting the globe. The Odyssey includes intense purification, the delicate art of fiber drawing, and the crucial stages of coating and cabling. From there, it undergoes exhaustive testing before being shipped and laid by specialized vessels. The result is a vast highway of light, an invisible architecture that allows billions of people to communicate, learn, and work with a simple click. Because of this network, a call across continents travels in less than a second, and the movies we stream arrive almost instantly. What feels so ordinary in our daily lives is powered by one of the most complex industrial processes on Earth, a hidden world of creation that most people never get to see with their own eyes.